First of all, I would like to tell you about a program called CRYSOL. CRYSOL computes the scattering of a given model and fits it to the experimental data. There are several ways how you can run CRYSOL. I prefer using the command line interface. This allows easily for scripting, etc. One can also use the web interface to run CRYSOL on our EMBL server. And another way of running CRYSOL is running it from the PyMol plugin called SAXS. If you have ATSAS installed on your computer, you can install this plugin and use it from PyMol. It looks like this, and it allows to run a number of programs using the practical graphical user interface. And another way of running CRYSOL would be using the program Primus. So Primus is a graphical user interface that allows you to analyze SAXS data and do basic data analysis and processing. So to run CRYSOL, you go to the Analysis tab, and then there is a button that says CRYSOL. And after clicking this button, the program will ask you to load a model or a number of models. Then the next step will be the configuration of CRYSOL. You can specify the angular units of your data. In this case, we loaded data in inverse nanometers, and there are a few other parameters. So the number of points is basically the number of points that the program will internally compute before fitting the scattering to your data. So, however, one of the most important parameters is the number of spherical harmonics. So in this case, we have 15. 15 is the minimum number you should be using, and you can increase it all the way up to 99. And the basic idea is that the more spherical harmonics you are using to approximate the scattering in solution, the more precise the scattering will be computed. However, the longer the program will work. Probably one thing worth mentioning is apply constant subtraction. That's an additional constant term that the program can adjust in order to compensate the improper background subtraction. All right, so let's start the program. Basically, it will run the command line version of the program in the background and will print some important information. Then you will get the fit of the model to your data. And the first question you should be asking yourself is this a good fit? The classical way of estimating the goodness of fit is computing the reduced chi-squared value, which is basically the square of the difference between the intensities of the fit and the experimental intensities, normalized against the experimental errors. This is important that we use the experimental errors that came with the data. Typically, this will be the third column in your experimental data file. And if these experimental errors are wrong, then your chi-squared value will be wrong as well. So if the experimental errors are overestimated, your chi-squared value will be way smaller than it should be. And if it is underestimated, your chi-squared value will be bigger. A simple way to check if your experimental errors are fine is taking two separate frames, for example, from the same pure solvent, and comparing them, applying this test. If you got a reduced chi-squared value around 1, then chances are that your experimental errors that came with your data are correct. So, but what is a good chi-squared value? In this case, we got a chi-squared value of 2.4. Does this mean that my model fits the data? The simple answer is that depends on the number of points that you have in your data set. So this data set consists of 500 points. And here there is a table that tells us that given the significance level alpha of 1%, the chi-squared values must be within these given ranges. So in this particular case means No, we have to reject the hypothesis that the two data sets computed from the model and the experimental data, they are the same optimum noise. So in this case, as you can see, there is a systematic difference between these two curves. A good way of looking at systematic differences between data is error-weighted residual difference plot. On a linear scale, we plot the difference between the fit and the experimental data points, normalized by the experimental errors. So here denoted with sigma. And there is another test that you can apply to see if there are systematic differences between the data computed from the model and experimental data. And this test is called the correlation map. Simply speaking, it will find the longest consecutive sequence of positive or negative differences. So here shown around 1 inverse nanometer actually. Then it will estimate the probability that this could have happened by chance, given the total number of points. And it will give you a p-value. Typically, this will be a p-value around 0, and acceptable p-values should be higher than 0.05. So how do we apply these tests? So it's very simple. You can run the Primus data comparison wizard. There's a button in the program Primus for that. And in this case, it will compare the two data sets and compute you the correlation map test p-value. So here we see that there are 47 points that are consecutively positive compared to the fit. And the estimated p-value will be ridiculously small. So, and this program will also execute the reduced chi-value test. And here we got the chi-value of 2.4 and also a ridiculously small p-value associated with chi-squared value goodness of fit test. So this is another case. This is a different model fitted to the same data. And here you can see that the residual difference plot looks much better. And the correlation map test p-value will be 0.06, which is above the commonly agreed threshold of 0.05. And you see that the button next to the p-value will be green, and the reduced chi-squared value will be 1.04, and you see that the associated p-value will be also in the green area.